right, so we're going to go ahead and start chemical bonding and molecular structure. So, good news about this unit is, I've looked at the multiple choice and the free response of the test, and like I said earlier, has to be the easiest test we've taken all year. Has to be. Okay? Like, I haven't seen a test that we've taken that has been easier than this. And if you can grasp this test, I am predicting that we should get really good grades on it. More than likely, we'll take this test, and your study session Saturday will probably be your last two test grades for this 9 weeks, I'm predicting. We'll probably go ahead and start on the last unit before spring break, but I highly doubt we'll finish it. So you'll have that test, and then you'll have the March 19th Saturday study session for a test grade for the fourth 9 weeks. And then we'll also have, what else are we going to have? Oh, like we'll do practice exams and things like that. That will count. So that's an overview for where we're at for majority of the years. We're on the downhill slide. Okay, this is almost over. All right, so what is a chemical bond? Bonds are attractive forces that hold groups of atoms together and make them function as a unit. Okay, most atoms are more stable and they have a lower energy if they are in a bond. That is why most atoms on the periodic table do not exist alone. They always exist in a compound. Okay, and that's because it makes them more stable. Bonding is going to relate to physical properties such as melting point, hardness, electrical and thermal conductivity, as well as solubility characteristics. So let's think about that. How would bonding relate to melting point? There you go. The stronger the bond, the higher the melting point. Okay? And the inverse is also true. The weaker the bond, the lower. There you go. Lower the melting point. Okay? And so we can relate those to hardness and all of the rest of those as well. Here's an important concept here. The system is achieving the lowest possible energy state by bonding. Okay? That's the whole reason atoms bond together. That's the whole reason they make molecules and compounds, is to try to achieve a lower energy state. So, if I am lowering my energy, okay, what do I do with the energy when it lowers? I release it, right? I just release it, okay? So, that means when we make a bond, energy is what? Released, okay? So, therefore, if I want to break a bond, what do I have to do? Add energy in, okay? So, it requires energy to break a bond. Those are important concepts too, okay? Now that is a huge misconception, and it's one that I hope I fixed last year, okay? But just in case I didn't, let's get it now, okay? When we form a bond, we become more stable, which means our energy state has lowered. That's the whole purpose, is to get to a lower energy state when we bond. That means energy is released. So if I want to break that bond, in turn, I'm going to have to turn around and put energy in to break it. Yes, ma'am?
But why does it become more stable? Is it because like they're like body weight? You know what I mean? You know what I'm saying? Like why does it become more stable?
Okay, we're going to get to that in just a second, but I'll answer it. Okay, so the question was, well, if you didn't hear it, is why does it become more stable when they bond? Think about it. So we're sharing electrons. Like let's say we've got carbon here and we've got oxygen here. So this line right here represents what? Two shared electrons, right? So these electrons, I'm going to draw them right there. There's the two negatives. They're being shared, okay? Not only are they being attracted by one positive nucleus, but they're also being attracted by what? Oxygen's positive nucleus too. When are electrons in their lowest state? When they are what? Closest to the nucleus, right? Okay? So in this case, these electrons here, okay? These electrons here are being attracted by two nuclei. So that means that's going to put them in an even lower state, because not only are they being attracted by one, they're being attracted by two. They're close to two positives. So that puts their energy even lower, which puts the molecule in a lower energy state. Does that make sense? Okay. All right. Bond energy is the energy required to break a bond. We have technically 3 types of chemical bonds. We talked about them last year. What were the 3 we talked about last year? Ionic, covalent. Oh, that's an IMF.
I don't see it on the board.
Everybody remember it? Okay, we remembered ionic. How do we know if a bond is ionic?
The positives and negatives.
We had a positive and negative. So normally that's a what? Metal bonded to a non-metal. Okay? A covalent bond is normally what?
Sharing a lot.
Shared electrons. So normally that's just 2 what bonded together? Non-metals. Thank you. Okay? That's 2 non-metals bonded together. So what's the only thing there you go. What's the only thing that's left? Metallic, which is how metals form. Okay? What we're really going to focus on though are just ionic and covalent. An ionic bond is an electrostatic attraction between ions. So electrostatic just means it's an attraction between something that is oppositely charged. Okay? So that's why this is normally between a metal and a non-metal, because metals form what kind of ions? Positive, thank you. And non-metals normally find what kind of ions? Negative. Okay, so there's that positive and that negative there. Okay, now, does it always have to be a metal and a non-metal? No. Okay, what if I had ammonium nitrate? Okay, these are 2 polyatomic ions. This ammonium is what? Positive, and the nitrate is negative. So what kind of bond is that? It's an ionic bond. Okay, that's the only time when it won't be a metal bonded to a non-metal. It still should be very obvious though, okay, that I've got a positive polyatomic ion bonded to a negative one. We see that? We're good? Awesome. Okay. Covalent bonds is when electrons are shared by the nuclei, and nuclei is just plural for nucleus, okay? That just means I got more than 1 nuclei. Careful here. Okay? Because sharing is hardly ever 50-50, okay? It's just like in real life. People are selfish. Very rarely do you find someone who's willing to be like, yeah, like you do 50% of the work and I'll do 50% of the work. Why is it that students hate group work sometimes? Okay? There's always that one person that ends up doing all of the work, okay? Atoms are like people, they're selfish, okay? There's always that one atom, okay, that pulls the electrons in more than the other one, okay? So sharing is very rarely 50-50. Okay? How do we calculate the energy of an ionic bond? We use Coulomb's law. Okay? Ooh, if we don't know Coulomb's by now, we should know Coulomb's after that last test. Okay? Everybody remember that? Where the force of attraction is equal to Q1 times Q2 divided by R squared? Yes? Yes, where R is the distance. Okay? And Q1 and Q2 are the charges. Okay? So if I want to calculate the energy of an ionic bond, I would just put their charges, divide by their distance, and multiply by that constant. Now, to my knowledge, you don't need this equation anymore for the AP exam because they took it off your equation sheet. Okay? But it is helpful to know this one. Okay?
Like, just like a free response,
Mm-hmm.
where they'll ask you to reference it.
Yeah, well, they'll ask you to reference it like last time. So, now, what sign should my energy be when I form an ionic bond?
Negative?
Negative, okay? It should be negative. How do I know that it's going to be negative? Okay, what are my Q values? Where do I get Q from? From the ion charges. If I form an ionic bond, one of them's going to be what? Negative, and one of them's going to be positive. If I do a negative times a positive, what do I get? Negative. Okay? So, that negative energy change just means my energy did what? Decreased. Okay? Which means my bond became more what? Stable. Okay? We became more stable because energy decreased. Okay? Now, could I use Coulomb's law to calculate repulsive forces? Yes. Okay. What if I wanted to show 2 electrons? Both of these would be what? Negative. A negative times a negative gives me a what? Positive. So if I've got positive energy there, that means I had to add energy in to get them to what? Stay. So is that repulsive or attractive? Repulsive. Does that make sense? You with me? Awesome. All right. Valence electrons are the outermost electrons. For the most part with us, we're going to focus on the s and the p orbitals. Okay? Those are the ones that make up your valence electrons. Now, let us review. How many valence electrons does everything in column 1 have? 1. How many valence electrons does everything in column 2 have? 2. We skip the transition metals. Dun, 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 dun. How many valence electrons does everything in group 13 have? 14? 15? 16? 17? 18? 8. Do we see this? Yes? This is important. You're not going to be able to draw them if you don't realize that. Okay, so make sure you know. Okay, and there we go. Chemical bond formation. There's 2 different levels of things that happen when we form these chemical bonds. So let's talk about the first one, okay? When 2 hydrogen atoms, we're just going to talk about a bond between 2 hydrogen atoms for this example, okay? But this same thing would work for every bond, all right? So when 2 hydrogen atoms approach each other, we get 2 bad energy things, okay? And bad is in quotation marks because there's really no such thing as bad energy and good energy, okay? It's not like energy has a soul, all right? It's just 2 not so positive things for us, energy things happen, okay? So when the electrons from both of the atoms get close to each other, they're going to do what? What do electrons do? Repel, right? So we're going to get electron-electron repulsion. And when those 2 positive nuclei get close to each other, they're also going to what? Repel, because like charges do what? Repel. But the positive nucleus from one of them is also going to be what to the other electrons? Attracted, and vice versa. So we get a repulsive and an attractive force. When the attractive force offsets the repulsive forces, the energy of the 2 atoms will decrease and a bond will form. So a bond does not form until the attractive forces overcomes those repulsive. Okay? That's where we get the idea of bond length, which is the distance between 2 nuclei where the energy is minimum between them. Why do I want the energy to be minimum? Because I'm trying to get to a what? Lower energy state. Okay? So, let's look at the graph. Why is a bond not, an optimal bond not happening here? They're too far away, so how does that affect my bond? There's no what? There's no attraction, okay? Now, why would this one be considered to be too close? The electrons are going to repel, and also the what? The 2 nuclei are going to repel, right? Okay? So here is where the attractive force overcame the repulsive force. Okay? So this is where, notice my energy did what? It went lower. So wherever my energy is going to be the lowest is where I'm going to get my bond length from. Do you see that? Okay. Here energy is too high. Then we go still too high, bam, there's my optimum. And if I kept moving closer, then my energy would go back what? Up. Do we see that? I know I keep asking you if you see it, but I need you to understand these concepts. All right, then we also have the orbital theory, which means when the electrons in the nucleus of one atom get close to the electrons in the nucleus of another atom, it's going to distort those electrons, right? Because as the electrons get close to each other, they're wanting to repel, but then as they're also getting close to the other positive nucleus, they're wanting to move towards there. So it creates a how would I say this? It's not a distortion. Disturbance. There we go. That's why I don't teach English. Thank y'all. All right, it creates a disturbance in that electron cloud. Okay, So then we're going to end up with two different orbitals, okay? We're going to get a bond orbital, which is where my electrons are going to be shared. Okay. And then I'm also going to get lone pair orbitals, where some of the electrons aren't shared, okay? They're just with one of the atoms, and so they're going to push away from where they're shared. Does that make sense? Because remember, electrons don't like to be what? Close to one another. So the ones that are just with the atom are going to push away from the ones that are shared. That's how we get the different shapes. Okay? That's why they don't all just lay flat. It's because these electrons don't like to be close to one another, so they try to get as far away as possible. Okay? That's what we're going to do Thursday. We're going to talk about those shapes. All right. So, the new bond orbital is built from the atomic orbitals of the two bonded atoms, and we're going to talk about that. So what we essentially do is we create new orbitals. You know how we've talked about how we have s orbitals and we have p orbitals? Okay? We're going to create sp orbitals. We're going to put them together. Yay! We're so excited. Okay? We're going to do it, and it's not hard. It's not hard. I promise. It's not hard. In fact, you did it last year. You did. We did hybridization last year. Except for Olivia, who did not do hybridization last year. But we're going to do it, and we'll talk about it. Okay, so the energy of the electrons in a bond orbital, and a bond orbital we're just talking about where the electrons are being what? Shared. Okay, is where the electrons are attracted by two nuclei, because they're being shared by those nuclei, right? This is what I was talking about earlier, Bella. Okay? That energy is lower than their energy when they were just attracted by only one nucleus. Okay? So that's why we get to that lower energy state. They get zapped by the nucleus. Okay? An ionic bond is when the bonding orbital is strongly displaced towards one of the nuclei. Okay? Now, is it going to be strongly displaced towards the metal or strongly displaced towards the non-metal? There you go. It's going to be the non-metal, because as I go across the periodic table, what happens to my effective nuclear charge? It increases. So that means it attracts the electrons more. So the electrons are going to be more attracted to the non-metal. When I get a covalent bond, that's when the bond orbital is more or less evenly distributed. Now, why would we say more or less? Because it's not 50-50. Okay, very rarely is it 50-50. In fact, I'll go ahead and tell you the only time it's 50-50 is if an atom is bonded to itself. Okay, obviously, if you bond to yourself, you're definitely willing to share things 50-50. Okay, all right. So, how do I decide if it's going to be shared 50-50 or unevenly? Well, we know it's going to be shared unevenly if they're different, but how uneven is it? Okay. The more shared unevenly they are, we'll go back here for a second, that means the more polar they are. So polar means we're shared unevenly. Non-polar means we're shared evenly. Okay. How polar are we? We get that from electronegativity. Now, we already talked about this exact picture with the same exact wording in the last set of notes. Okay, so we didn't use it a lot though. Why? Because we can only talk about electronegativity if we're talking about an atom in a molecule, which means that atom has to be participating in a what? Bond. Okay, so electronegativity is the ability of an atom to attract shared electrons to itself. Okay, so how do I look at a periodic table and figure that out? Electronegativity increases like this as we go up. Okay, so the most electronegative would be fluorine. The least electronegative would be francium. Huh? I don't think so. The question on the test had to do with radius, I think. Okay. So, which is the same thing actually as electronegativity. It follows the same rules. Why? Because why is fluorine the most electronegative? has the highest effective nuclear charge and the smallest radius, which means any electrons in fluorine are going to be very attracted to the nucleus, right? Yes. Why is francium the least? It has the lowest effective nuclear charge and the largest radius. So any electrons with francium are going to be so far away from the nucleus, there's going to be very little what? Attraction. Okay? So fluorine is going to have the greatest ability to attract electrons to itself. Francium is going to have the least ability to attract electrons to itself. How do we use the electronegativity difference? If I'm using the difference, that means what am I doing to the electronegativities? What does difference mean?
So subtract.
Subtract, okay? So if I'm looking for the difference in electronegativity, I'm just subtracting the electronegativity. See these numbers? Francium 0.17, fluorine's 3. You see that? Those are their electronegativities. Okay? So I can look at the difference in them and say, okay, if the difference is greater than 1.67, it's an ionic bond. Okay? If the difference is less than 1.67, it's a covalent. But we know with a covalent bond, they can be what? Polar or nonpolar. If the electronegativity difference is less than 0.4, we say it's nonpolar. If it's greater than 0.4, we say it is polar. You see that? Yes? This is easy? You feeling good about this? So, let's look at exercise 1. Exercise 1 says, order the following bonds according to polarity. Okay? What they're saying is they want us to go from nonpolar to polar. Okay? Well, which one up here can you definitely tell should be nonpolar? HH, right? So, because if I look at the electronegativity of hydrogen in the notes, okay, it's what? 2.1. So if I take the difference between the two hydrogens, the difference is going to be what? 0. Because 2.1 minus 2.1 is 0. So I know the electronegativity difference there is going to be 0. So HH is going to be most nonpolar.
Will they give
Right.
us a chart with their electronegativities, or will they give it to us a problem like what their electronegativities?
They might, but then I'm going to show you how you can figure it out without having the numbers. Okay? So here's how we would do it if we had the numbers. So now I see oxygen and hydrogen. So I can look on the table and I say, okay, well, oxygen is what? 3.5. Hydrogen is 2.1. So what's the difference between them? 1.4. Okay? Does everybody see how I did that? Because I'm going to cheat and go ahead and fill in the rest of them without looking to save time. So this is 0.9. This is 0.4. This is 1.9. Okay? So can I rank these from nonpolar to most polar? Yes. What would come after HH? SH?
Then the
CLH.
OH.
Okay. Now, how could I figure this out without using numbers? Okay. Do I know the trend of electronegativity? Yes. Okay. So let's look at this. Let's pretend like there's not any numbers on here. Okay. The most electronegative element on the periodic table is who? Fluorine. So the hydrogen-fluorine bond should be the most polar, right? Because it's going to be the biggest difference. So if I look at the so here were my choices. I know hydrogen's going to be the lowest, right? So then I'm looking at the 4 of these to determine which one is going to be the next most nonpolar. Well, it's going to be SH. How do I know that? Because sulfur's on the bottom and it's towards this side. Because how did we say electronegativity increases? This way, right? So it would go this one, then this one, then this one, then this one. Do we see that? So we can look at it using the periodic table and come up with the same exact answer, and it is correct. Okay? All right, so to sum it up, when two nuclei are the same, like HH, the sharing is equal, and we say the bond is nonpolar covalent. Okay? when two nuclei are different, any of these, okay, the electrons are not shared equally, giving us slight poles, and I want you to underline slight several times, because we're going to talk about that, which means it's polar. And when the electrons are shared very unequally to a great extent, then we say it is ionic. Okay, now let's talk about that slight. Why do I care about it being slight? Because I don't want you to think it's a definite positive and a definite negative. The only bond that has a definite positive and a definite negative is ionic. Okay? Polar covalent is slight. So let's talk about that bond between oxygen and hydrogen. Okay? Now, which one is most electronegative, oxygen or hydrogen? Oxygen. So who's going to pull more electrons towards itself? Oxygen. So that means my hydrogen are going to left to be slightly what? Positive, because the electrons are being pulled away from them. And it's going to leave my oxygen to be 2 slightly negative. Okay? Why is it going to be 2 slightly negative?
It's got 2 pairs. No?
Not because it has 2 lone pairs.
Because it's got two lines.
Because it's pulling electrons from 2 different hydrogens. Do we see that? Okay. Now, is this a definite positive or a definite negative? No, not at all. Okay? That's why we use these little symbols here, and they mean slight. The only time you can talk about a definite positive and a definite negative if I'm talking about an ionic bond, like sodium chloride. This sodium is a definite positive, this chlorine is a definite negative. We see that? Okay. And how do I know that's a definite positive and a definite negative? Sodium's a metal, chlorine's a non-metal. That's my first clue. That is the first thing you should look for when you're trying to figure that out. How do I know these are slight? Because oxygen's a non-metal and so is hydrogen. We've got 2 non-metals. Do we see this? Yes? Okay. All right, ionic bonding. When we do the ionic bonding, which just means we've got the what? Positive bonded to the negative, we get a crystal lattice. What do I mean by that? Look at your pictures down here. Okay? This means they're not actually bonded because they're sharing electrons. They're bonded because I've got my negative that is very strongly attracted to my what? Positive. So they just keep stacking up on top of each other until they form a lattice. Okay? Which is a lot of times why we get the crystals. We call it a crystal lattice. Like salt. Salt is a what? Crystal. We call it salt crystals. Right? Yes? Yes, ma'am.
Rock candy?
Yes. But that's a little bit different. Okay. All right. So, here we can see the energy change that happens when we combine them. The enthalpy of dissociation. You have a study session Saturday, and they're going to talk about enthalpy. Does anybody remember what the symbol for enthalpy is? That's entropy. H. Okay? Enthalpy is H. Enthalpy is the what?
It's for
Oh, it's
the
just
energy
concentrate?
required.
Energy. Okay? Enthalpy is just the total amount of energy. Okay? What's the difference between delta G and delta H? Delta G is the amount of energy available to work. Delta H is just the total amount of energy that's there. Okay? The only reason why I'm pointing that out is because you're going to see it Saturday. Saturday is all about thermodynamics. Hope likes that. Okay? All right, so enthalpy of dissociation. What happens when something dissociates? It breaks apart. So enthalpy of dissociation is energy required to, you can change decompose to break apart an ion pair. Okay. The more energy it takes to break them apart, that means the bond was that much what? Stronger. Okay? How can I figure out how strong the bond is? By looking at my Coulomb's law. Okay? For example, when we did CaO versus K2O on your test. Okay? Remember we said that CaO, all right, had a more negative lattice energy. What do I mean by lattice energy? Lattice energy is the energy released when the bond formed. All right. Can't hardly read that, so I'll say it again. Lattice energy is the energy released when the bond formed. Okay? CaO had a more negative lattice energy, which means CaO released more what? Energy. Which means it's going to require more energy to get CaO to what? Break apart. Okay? How do I know that? What is my Q1 and my Q2? Charges. Okay? What's the charge of Ca? Positive what? 2. How do I know it's positive 2? It's in the second column. Oxygen is a negative 2, which you should have memorized. Okay? Potassium is what charge? Positive 1. How do I know it's positive 1? It's in the first column, whereas oxygen is a negative 2. So, where would I put these positive charges and this negative charge? I would put them here, right? So, when I multiply 2 times 2, or I multiply 1 times 2, which is going to give me a bigger number? 2 times 2. So, it's going to require more energy to break CaO apart than it is K2O. Do we see that? Yes? We can also look at the distance, because we're dividing by the what? Distance. Okay? Which one is bigger, potassium or calcium? Potassium's bigger. How do I know potassium is bigger? Calcium has a greater what? I'm going across effective nuclear charge. Okay, calcium has a greater effective nuclear charge, which means it pulls its electrons in closer, right? So that means the distance between potassium and oxygen is going to be greater than the distance between calcium and oxygen, right? Okay, so the closer I can get them, better off we are, correct? Yes. So, to sum that up, the energy of attraction depends directly on the magnitude of charges. So the higher the charges, the greater the attractive energy. Okay? And the greater the distance, the smaller the attractive energy. Let's go to covalent bonding. All right, so most things covalently bond, actually, instead of ionically bond. So more things covalently bond, which is kind of ironic, because the nonmetals are the least represented group on the periodic table, but we get more covalent bonds than we get anything. So there are 3 major things to discuss, but the first one we're going to start with is the localized electron bonding model, and I'm hoping we're going to get time today to start on that, because it's my favorite. I love it. But we'll see. So this is just assuming that we are binding, I guess that we're binding the atoms together by them sharing electrons, okay? And which electrons are they going to share? They're valence electrons. Why are they going to share their valence electrons? Because those are the electrons that are there to share, okay? They're on the outside of the atom. Are we going to like crush together and share the inside ones? No, okay? So we're going to share them off. So we're either going to have lone pairs in this model, and we're also going to have bonding pairs, where again, lone pairs just means they're not being shared. Okay, they're just with one atom. And a bonding pair would mean those electrons are being shared. Yes? Yes, nod with me. Nod with me. Yes. Did you get your notes? Oh, you did? Okay.
I mean, I don't remember all this stuff.
No, it's okay. You're good. I was making sure you got them because I didn't know if I put them on your desk or not. All right, so we're going to look at Lewis structures to describe how the valence electrons are arranged. Okay, and then we're going to use VSEPR to predict the geometry. Okay, and if we can get further along today, maybe I can start that tomorrow, so y'all won't completely miss all of it. Okay, and then of course we're going to start talking about how the atomic orbitals blend doing hybrids, but that's the next set of notes. I love hybrids. They're good. They're good times.
Are you?
Yeah, they're easy. They really are easy. Like, you're going to be like, oh, I can't believe I dreaded that. That's really easy. Okay, so how do we know how many bond pairs we're going to have? Because we're going to use the octet rule, which just means everybody wants what? 8. Okay. How do we draw them? We use a dash to represent the shared electrons, and we use dot dots to show the lone pairs. This should be review. You've drawn these lots. Okay. Now, single and multiple bonds, I'm going to put a star beside this because college professors love it. Okay, so to be honest with you, this is not going to show up a lot on your exam, but I do want you to know it when you get to college because they love it. So, hey, it's actually something that's really easy. I did not get it when I was in college for some reason, and now I feel like, I don't know, a ding-dong because I should have gotten it. All right, so a single bond is when one pair of electrons are shared. We've talked about this before, right? Okay. This means that we would call this a sigma bond. And a sigma bond just means that the orbitals collide head-on. Okay? So they're sharing the electrons head-on. Okay?
How do they change the sign for sigma?
Okay. A double bond is when two pairs of electrons are shared. So that means the double bond is going to have one sigma bond, and then it's also going to add in a pi bond. So instead of them sharing head-on, it's like the orbitals overlap, okay, like on top and on bottom. Okay. A triple bond is when three pairs of electrons are shared. So that means there's one sigma bond and two pi bonds present. Okay. Combinations of sigma and pi are stronger than sigma alone. Pi bonds are weaker than sigma bonds, but together they're stronger. Okay? So, when we have multiple bonds, we increase the electron density between the two nuclei. What do I mean? Okay? I'll show you this. I'm going to draw 3 different molecules for those of you who like to keep up. Oh, whoops. I did that wrong. Let me redraw this. Sorry for those of you using a pen. There you go. So we've got the single bonded carbons, we've got the double bonded carbons, and we've got the triple bonded carbons. Right? Right. Okay? When I increase the electron density between the two nuclei, so that just means I'm increasing the number of electrons, the nuclear repulsions decrease. Okay? What do I mean by that? Nuclear means I'm talking about the what? The nucleus. Okay? So I've got a positive nucleus here with this carbon and with this carbon. The only thing separating these two positive nucleus is how many electrons? 2. Okay? Whereas when I move to a double bond, how many electrons are separating the two positive nucleus? 4. So therefore, the nucleus of the double bond is going to be less repelled than the nucleus from the single bond. Do we see it? The electrons are kind of providing a buffer between the two nuclei. Does that make sense? Okay. And by the time we move to the triple bond, now I've got how many electrons separating them? 6. Okay. So that means these nuclei in the triple bond can move closer together. Okay. So that makes my bond length shorter. So that makes which of these bonds the strongest? Triple. Then I would say the double. Then I would say the single. Does that make sense? Do we see that?
Or stronger because they're closer together.
Yes. Because there's a greater number of electrons between them, so it decreases the repulsion between the two nuclei. If I was asked to explain that on a test, that's what I would say. Okay. So, what they would ask you on a test in college is the professor would say, let's just say he gives you this molecule here. Okay. And they would maybe choose one bond, choose multiple bonds. They're going to say, okay, what type of bonds exist here? So what type of bond exists between the carbon and the hydrogen? Sigma, right? Because it's just a single bond. What's the only type of bond that can be experienced by a single bond? Sigma. What about between this carbon and this hydrogen? Sigma, right? This is a triple bond. What type of bonds are going to be right here?
2 pi.
A sigma and 2 pi bonds, right? Do we see that? That's honestly all you need to be able to do when you get to college, when it comes to sigma and pi. Is you need to understand that a triple bond has 1 sigma, 2 pi. A double bond has 1 sigma, 1 pi, and a single bond can only have sigma. Okay. We see that? So when we get to college, that's not going to mess us up. No. Yes, ma'am. All right, and then coordinate covalent bonds should be a review for you because this comes from Lewis acids and Lewis bases. Okay? Remember how we talked about there's some people that come to the party without bringing any snacks but still eat everything? Yes? All right, that's what we talked about with coordinate covalent. So there's one, like here, this is ammonia. Ammonia is base or an acid? It's a base. Okay? All right, ammonia is a base. Remember we said NH3. That's one thing I can always count on. That's always a what? Base. Okay, it has a lone pair. Hydrogen comes along. Does it even have any electrons? No. So if they're going to form a bond, that means nitrogen has to do what? Share both. Okay? So when they form a bond, notice we show that by using a what? Arrow. That lets me know that's a coordinate covalent bond. It's not a regular covalent bond, it's a coordinate covalent. How do I know it's a coordinate covalent? Because nitrogen brought both snacks to the party. Okay, it brought both electrons. And hydrogen's having to share it. So you can put a positive next to that hydrogen to show it didn't have any, or you could put the whole thing in brackets and put the positive on the outside instead of the inside. Either one's acceptable. Okay. I normally put it in brackets and put the positive on the outside. All right, exceptions to the octet rule. Okay. Hydrogen only wants 2 electrons, and that also goes the same for helium. Okay. Beryllium is okay with only 4 valence electrons, and that also goes the same for lithium. And boron is okay with only 6 valence electrons. Okay. Now we've already said almost everybody wants what? 8. But sometimes we can also get an expanded valence, which means we can have more than 8. And this only happens with atoms that are in the 3rd period or greater. Okay? Why can it happen in atoms that are in the 3rd period or greater? Because what kind of orbitals are in the 3rd energy level? I can have S, I can have P, and I can have D. Okay? So if they're in the 3rd period or greater, that means they can expand into the D orbital if they need to, which means they can have more bonds. Does that make sense? Okay? If I only have S and P, like I have in the 2nd period, okay, all I have is S and P in energy level 2. That means I can only fit a maximum of what? 8, right? But if I add a D orbital in there, then I can add more electrons, right? 10 more. Okay. And then a few times you can have an odd electron compound, but we're not focused on those.
Is that like a set number, 10, if you throw a D in there?
Yeah. You wouldn't be able to add more than 10. Because Ds can only hold 10.
Make sure you don't like y'all's exception.
Oh, I do need to point this out before we move on to the next thing.
See,
Sorry. The only ones that can... Oh, no, that's the next thing. I didn't miss it. I thought I missed it. I didn't miss it. I'm good. All right. It's on this, not that. All right. So, drawing Lewis structures. My favorite. I love this unit in pre-AP and I love this unit in AP because I love drawing them because I don't know why. I just love it. So, everybody get excited. Yay! Big smiles. Yay. We're excited. Here we go. All right, so a few rules, and then maybe we'll have time to draw a couple. Probably not. Sad face. But we will tomorrow. All right. Hydrogen is always a terminal atom, which just means hydrogen is never in the what? Center. Okay? Hydrogen's never in the center. Okay? How do we decide who's in the center? The atom with the lowest electronegativity. Can I look at the periodic table and figure out who has the lowest electronegativity? Yes. So a lot of times we just say the oddball element, whichever one there's less of has to go in the middle, which is normally true, but if you get stuck and you can't figure it out, the lowest electronegativity. Okay? So how do we draw it? We add up the group numbers of the elements. Okay? And if it's a negative ion, then I add whatever the charge is. If it's a positive ion, then I would subtract whatever the charge is. And then I would divide by 2 to get the number of electron pairs. Place one pair of electrons, or a sigma bond, between each pair of bonded atoms. Then subtract from the total number of bonds you just used. Everything left over, we're going to place lone pairs around each terminal atom to give it, how many does it want? 8. Okay. And then if I have any left over, they go to the central atom. If the central atom is from the 3rd period or higher, then it can accommodate more than what? More than 4 pairs. Here you go, Jeb. This is what you wanted to know. It can accommodate up to 6 pairs. Can't go past 6 pairs, so there you go. If the central atom does not yet have 4 electron pairs, because remember, if it's in the center, it still wants 8 as well, right? Yes? Then convert some of the terminal atom lone pairs to pi bonds, which means we've got to make them what? Double and triple. Okay? The only ones that can form double and triple bonds are carbon, nitrogen, oxygen, phosphorus, and sulfur. Got it? Let's try it. Do we have time? No, we don't have time. All right, so when you get here tomorrow, we'll start drawing.